So, today I will discuss about the viscosity of liquid, how to measure viscosity of a liquid. So, that is what I will discuss today. So, you know viscosity, viscous force, uh, basically when liquid move. So, it's it's it does not move it does not move freely. What I mean this, if liquid is in velocity in liquid, okay, so when it moves then it feels friction force opposite to the motion. Okay. So, it is a very simple example. If you put a ball, small ball in a liquid, when that ball will go down, means ball will move, then this ball will feel friction force due to the liquid. So, that is the called the viscous force. Okay. So, whenever something is in motion in a liquid, so it feels frictional force due to the liquid. So, that force is called the viscous force. Okay. Now, we want to determine the viscous force, basically viscosity of a liquid in the laboratory. So, viscosity of a liquid, it is that we tell the coefficient of viscosity of liquid. So, so basically our experiment is determination of coefficient of viscosity, coefficient of viscosity of a liquid. So, basically in our laboratory we will measure the viscosity of water. Okay. So, this definition of viscosity, coefficient of viscosity, say it is eta, it is equal to viscous force per unit area divided by dV by dr, that is the velocity gradient. Okay. And one negative sign is there, Okay. Why negative sign? Because this actually dV by dr, there is the velocity change between layer to layer. Okay. So, water is in moving, water is in motion. Okay. So, if you take different layer of water, if at a certain layer, say here it is contact with a static surface. So, here velocity is 0 basically. Now, if you, so this velocity of this layer, velocity of this next layer are not same, there is a velocity gradient. Okay. There is a velocity gradient. So, this we are telling this velocity gradient is dV by dr. Okay. If I distance, if I take from here, so it is if we measure distance from here, so if we go up, so it is just changing r. So, here r equal to 0, here r equal to 0. So, its a velocity gradient is basically it is negative. So, when you are going in, r is increasing, velocity is decreasing. and at the center here we can take the velocity is maximum, okay, or some velocity v, and when you are going to this static surface. So, velocity is going towards 0. So, that is why this dv by dr is negative. So, that is why this negative sign has come. So, this is the definition. Definition is the viscous force, F is viscous force per unit area per unit velocity gradient. Okay. So, that is the definition of coefficient of viscosity of a liquid. Okay. So, now I want to measure this coefficient in a laboratory. So, whenever you want to measure a parameter for a particular parameter is which represent the property of a material. Okay. So, you have to take a particular geometry, and for that geometry you need working formula. Okay. So, it is the definition, it is not the working formula for the experiment. So, for same I think this for the same measurement of this coefficient. Okay. So, people can do in different ways, means people can design its own experiment. So, depending on the geometry of the experiment, one has to find out this working formula for this eta. Okay. So, here in our laboratory we will use this capillary tube. We will take a capillary tube. It has say length L. It has say length L, and its radius is capital R. Okay. And now liquid is flowing through this capillary tube. Liquid is flowing through this capillary tube. Now, liquid will not flow automatically, right? If it is perfectly horizontal, liquid will not flow automatically. You have to, there should be pressure difference between these two phase. Okay. So, you have to apply pressure difference. So, here say pressure is P plus del P, and here this pressure is say P. So, pressure difference is del P. Because of this pressure difference del P, so liquid will flow. Now, when liquid will flow, then so you will get basically cylindrical. So, this liquid in this capillary tube, it is in cylindrical form. So, you can consider concentric many cylindrical liquid. Okay. So, its surface is basically cylindrical. So, let us consider a surface, let us consider a cylindrical one liquid surface. Okay. Okay. At distance r, small r from the center. So, this is the center. So, this is the center. Okay. This is the center. So, from here this distance is r. So, here we are taking basically this distance, this origin here on this axis, and this way this distance r is changing. Okay. So, its maximum, this distance is here, it is r, capital R. Okay. Now, due to this pressure difference, there will be so here what is the, so when liquid is this layer, it is not, it is the basically cylindrical layer. Okay. So, when it is moving, so there will be viscous force in opposite direction. So, we are writing that force is F viscous, F viscous. Okay. So, F viscous. So, this F viscous force is in this direction, and F due to this pressure difference there will be force in this direction, in opposite direction, okay, because of this liquid is flowing. So, this force, if I write F pressure, force due to this pressure difference, F pressure. So, what will be that force? This is basically del P, this is the pressure into the area. What is the area on this? So, pi r square, pi small r square. Okay. So, this is the force acting on this liquid column, okay, due to this pressure difference del P. Okay. Now, and then this due to this viscous force, so that will be that is in opposite direction. So, that viscous force, so that is basically here viscous force as I told. So, this will be eta minus eta A, okay, let me write dV by dr into A area. So, this area is basically this is the surface area of the cylinder. So, it should be because this eta, this force per unit area is basically surface area of the water, of the liquid. Okay. So, is the cylindrical that surface 2 pi r and then L, length is L. So, this will be the viscous force. Okay. Now, this force will be equal, okay, or net force on this will be equal when there will be steady state flow of water. Okay. In steady state flow of water. So, this F pressure plus F viscous is 0. Okay. So, if you equate these two, yes, if you equate these two, so you can basically write dV by dr equal to, so minus sign will go this here, this plus this. So, you take in opposite side, dV by dr equal to del P pi r square divided by eta 2 pi r L, right. So, this basically you are getting delta P, pi will go, r this will go by 2 eta L, okay. So, here dV by dr equal to del P by 2 eta L. So, dV by dr equal to delta P by 2 eta L. So, del P find whatever the pressure we are applying between these two end of the capillary tube. L also length is known, we will measure the length. Now, what is dV dr, dV by dr, how to measure it? So, directly we cannot measure it. So, you have to go further. So, here if I integrate this one, let us find out the velocity of the liquid. So, if you integrate dV by dV del P by 2 eta L, I think one r should be there. Yes, I think here one r should be there, one r is left. So, there should be R1 here, there should be R1 here, there should be R here. So, your R dr. Okay. So, now in cylinder velocity here is maximum at center, but here at r distance it is some velocity v, and at capital R distance velocity is 0. So, if I integrate over this say r to capital R, so capital R velocity 0, here velocity v in general. Okay. So, then you have to integrate, and if you integrate, so here if you integrate, so I think v velocity as a function of r, okay, velocity are not same. So, from center if you move towards the surface, so velocity will change, velocity will decrease basically, no, r will increase, velocity will decrease. So, here basically you will get del p by 2 eta L, it is the eta, and here you are getting r square by 2, r square by 2. So, I will get I think, yeah. So, this there will be minus sign, there will be minus sign, anyway to forget the minus sign, just you write r square minus r square by 2. Okay. So, this is the expression we got. So, this v as a function of r is this. So, this v is the velocity of the liquid. Okay. Now, problem is again velocity of the liquid at different layer, how I will measure. So, this is the again difficulties. So, further if we proceed, this velocity now is see continuity of basically if you consider the continuity equation of continuity. So, you can say think that overall there is a velocity distribution in this tube, but per unit time whatever the liquid will come out, volume of liquid say V is the volume, and it is and if you collect the water in time t. Okay. So, water is flowing through this tube. Now, if I collect water for time t and see this volume of this liquid coming out, that is V. Now, this V is related to this the volume, no. So, volume is basically liquid here, you can consider this area pi r square. So, liquid is coming out through this area, okay, pi r square, and then per unit time what is the length it is traveling. So, that is the basically velocity of the liquid. Okay. So, average velocity of the liquid V r, okay, or V, if I write V is a function of r. So, here I can tell this this the volume of the liquid will come out per unit time. Okay. So, this is the volume of liquid will come out per unit time. So, yes. So, this I can write basically. So, this is basically in integration form, or it is change of volume. Here basically this whatever water is coming out, this per unit times. Okay. So, this I can write dV by dt. volume change per unit time or volume coming out per unit time. So, this is dV by dt equal to I can. So, through this tube I can write the velocity v, this I should write like this, okay, to differentiate volume and this. So, this dot dA area and this integration, because here problem is this way I cannot write this because velocity is not constant, it depends on the radius, you know. So, that is why I have to take small yeah. So, I have to take in differentiate form. So, this and then basically that this velocity at this point and from the and area, if you in that area, in this region, if I consider just small area and through this area what is the water is coming out per unit time. So, that is this. Now, I will integrate over this over this whole area. So, this A is basically pi r square, okay, pi r square. So, over the r 0 to r I have to integrate. So, if you integrate, so this V r is basically this V r here. So, if I put it, pi r square is there, if I integrate. So, I am not doing, just you can do it. So, I will get this relation, I will get pi then del phi divided by 4 eta L and here r square is there and here I think here this V r, this r square minus r to the r square. So, this r to the 4. So, if you consider them, so finally your result will be 8 eta L, 8 4 and 1 2 will come here. So, this basically r to the power 4. Okay. So, this will be the final expression, and based on what? Based on this formula, based on that in capillary tube water is flowing between pressure difference del phi, and then if its length is L and radius is r, then the water volume of the water per unit time will come out from this tube is related like this, okay. And this del V by del T. So, this I can write V by T, okay, over time T, this how much volume is coming. So, this is the rate of change. So, if I collect for time T, okay, then what is the volume? So, this is the V. Now, then eta you can write, I think 8, no, here eta, I will take eta, then pi r to the power 4 del phi, then V will come and 8 is there, L is there and also T will be there, okay. T will go off T and T, okay. So, that will be the formula for this. Now, here you see the basically this equation is called Poiseuille's equation. Okay. So, somebody has, you see, to determine the coefficient of viscosity of liquid. So, somebody has done has worked out this method, okay, and find out this working formula. So, using this working formula, one can calculate or determine the viscosity, coefficient of viscosity. Okay. So, what I want to mean, so what is viscosity, what is coefficient viscosity, so the definition is there, but if you want to measure, so in different way one can measure. So, one can design itself, and for that, depending on geometry, one has to find out the theory. Okay. So, here this Poiseuille's, he suggested that if you design the experiment like this, so that will be the working formula for that geometry of the experiment. Now, this is ready made, it is in our hand, given by Poiseuille's. Okay. Now, in laboratory we have to exactly whatever the now interesting thing is that we have to create, or we have to find out, or we have to build up exact geometry of the experiment depending on the condition of this expression. Okay. So, in next class I will demonstrate this experiment in the laboratory. So, in the laboratory, so we have to take a tube, okay. Now, we have to make arrangement to create pressure difference. So, manometer generally we used to make pressure difference in these two end. Okay. So, this depending on the liquid height difference. So, we create this basically pressure difference del P. Okay. So, for manometer we can take this reading. So, this del P will be actually rho GH. So, H is the basically difference of these two water level. Okay. So, that way del P will get, and then radius r. So, we have to measure the radius of this r, okay, of this tube, this internal radius of course. So, we will use either travelling microscope, or we will use mercury, okay, to measure this radius, internal radius of this tube. So, that we have to experimentally measure, and length also using meter scale we will measure, and then only now over taking the stopwatch we will collect water, okay, for different time t we will collect water, for different time t we will collect water. So, then from the basically measuring cylinder, volumetric cylinder, you can measure the directly volume, or you can measure the mass of this water and then just divided by this density of the water, then that will give this volume. Okay. So, I will show you this the experimental setup in our laboratory, and how we are measuring these parameters to find out this viscous coefficient of viscosity. Okay. So, for any experiment this is very important to understand the working formula, because working formula has derived based on a particular geometry, and using this working formula if you are going to do experiment. So, in laboratory you have to create same environment in the experiment where this working formula was derived. Okay. So, that is why derivation of the working formula is important to understand. So, that is what I discussed, and now we will follow each and every step in the experimental geometry to measure the individual parameters and calculate the eta. So, I will stop here. Thank you.